Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the lecture 4 of module 10. In lecture 4, we are going to discuss about interseismic deformation and seismic cycle. The topics that we are going to cover today are interseismic deformation and the seismic cycle, within which we will be studying about interseismic shear strain rate and advantages of geodesy, and then we will be having the summary of today's lecture. As far as the recap of previous 3 lectures of module 10 are concerned, the review goes like this. Geodetic methods using signals from space permits all 3 components of position to be measured to sub-centimeter precision and now give coseismic motion to high precision much more easily than was previously possible. There are 3 techniques are popular. Very long baseline interferometry, in short it is known as VLBI, satellite laser ranging SLR, and global positioning system GPS are popular geodetic techniques to measure ground deformation. GPS uses a constellation of satellites transmitted coded timing signals on a pair of microwave carrier frequencies synchronized to very precise onboard atomic clocks. GPS data can be obtained for continuous period of time or short period of time. So basically you can have continuous mode or the survey mode, and in the continuous mode you will keep the instrument at a place for a longer duration, and in the survey mode you will go and visit the site after some time and then take out the instrument after you are done. So GPS data can be obtained for continuous period of time or short period of time. The later one, that means the survey mode, is cheaper. The biggest limitation of geodetic data for earthquake studies is that the positions of geodetic markers before the earthquakes are needed. For radar, D is the antenna length. So a radar a distance r above the earth's surface could resolve object of size x, where theta in subscript d is equal to lambda by d is equal to x by r. The phase difference between radar signals with wavelength lambda reflected from the earth's surface and recorded by antennas at position a1 and a2 is phi is equal to 4 pi by lambda r2 minus r1, where R2 and R1 is the range from the antenna at AI to the reflection point. If differences in the satellite positions between the measurements are removed, a vector surface displacement d causes a phase change, and this phase change will approximately be equal to 4 pi by lambda delta r, where delta r is d dot r cap. And delta r is the projection of the vector displacement along the look direction connecting the satellite and reflection point. The results are shown as a phase difference map called a differential interferogram. Then we talked about static coseismic displacement, and static coseismic displacement contain 1 by r squared term compared to 1 by r term for propagating waves. Thus it decay more rapidly with distance from the earthquake. For infinite length fault, the fault parallel displacement in x direction and the slip or the deformation in y direction uy varies with distance from the fault y, as uy is equal to plus minus capital D by 2 minus D by pi tan inverse Y by W. W is the rupture depth of the fault and D is the depth of the fault and Y is the distance from the fault. For finite length faults, the displacement tapers off rapidly past the fault ends. If a fault is buried and extends from depth W to depth capital W, we also discussed about the buried fault, also known as blind fault. It has certain depth after which its exposure basically can be felt. So it is not exposed on the surface. So it has a depth around W, small w, and it is extended to a depth of about capital W. And in that case, the displacement Uy will be equal to D by pi in bracket tan inverse Y by W minus tan inverse Y by capital W. A fault that does not reach the surface, the displacement is both reduced in amplitude and varies more smoothly with distance than it would for a fault extending to the surface. Estimation of fault parameter using geodetic data is an inverse problem and has highly non-unique solutions. As we have discussed about, geodetic data can be used to find out the fault parameters and it can be used to identify the nodal planes such as the fault plane and the auxiliary plane, but that cannot be resolved using the seismic data or the earthquake data. So if we are using both the data together, then they may be complementary to each other and can resolve the model with better accuracy. That means less amount of non-uniqueness. Seismic waves has an ambiguity in distinguish between the fault plane and the auxiliary plane. The geodetic data do not, as static displacement models, do not have nodal plane perpendicular to fault plane. We use strong motion data, teleseismic data and geodetic data that provides good constraints on fault geometry and slip on it. Geodetic data that depend on the difference in position before and after an earthquake provide no information about what happened during the earthquake, whereas seismological data can sometimes show how the rupture evolved. So this is the benefit of using both the data together. If you are using the data such as the geodetic data and the seismological data alone, then they will not complement each other and the model that you will get will be associated with high amount of uncertainties. In case you are using only the seismological data, then you will not be able to resolve which one is the fault plane and which one is the auxiliary plane. But in case you are using both the data together, then you can easily find the auxiliary plane and the fault plane. The result for the different data types differ because each is sensitive to the different features of the slip. In post-seismic, slip deformation goes on silently without a seismic signal for some time after an earthquake and it seismologically observed. So now let's start with today's lecture where we are going to talk about inter-seismic deformation and the seismic cycle. And if you look at this figure, you have seen this figure previously as well in case of elastic rebound theory, which was given by H. Reed in 1906. So if you look at this figure, you can see there is a fence, there is a fault boundary, and you can see there are the two blocks which are basically moving in opposite directions in a strike slip fashion, and the strain is keep on building up. The far field side is moving, but the material near to the fault is not moving. They are locked with each other in the second picture. And in the third picture, after the co-seismic event happens, then the displacement near to the fault catches up with the far field motion. So geodesy gives insight into the seismic cycle before, after and between earthquakes, whereas we can only study the seismic waves once an earthquake occurs. So this tells us about the seismic waves has some drawbacks. So seismic waves will only be generated after the earthquake is occurring, when the earthquake is occurring. But geodesy gives us the insight about the rupture process, about the faulting process, even before the earthquake is happening and after the earthquake is happening and in between the earthquakes of the seismic cycle. Consider a simple elastic rebound model of an infinite strike-slip fault at a plate boundary, assuming that large earthquakes release all the strain which accumulates between the earthquakes. So we just discussed. So the far field side, the accumulating the strain, but there is no displacement at the fault. But once the co-seismic motion occurs, then the material near to the fault catches up with the far field motion, and the displacement at the fault plane, at the fault, is basically gets equal to the far field motion. After an earthquake, material on the right, that means positive y side, far from the fault, moves at far field rate v relative to minus y, left side of the fault, so has moved a distance vt by time t. However, between earthquakes, the fault is locked down to the depth w, although it slips freely below. So material at the fault does not move between earthquakes. So if you look at this picture here, you can see this is the co-seismic and the inter-seismic slips and the strain, and there is this total displacement here, or you can say total slip here, and that is at the plate boundary, and there is this co-seismic motion, that is the deformations at the co-seismic event during the earthquake. And if you want to find out the inter-seismic deformation, then you will have to subtract the co-seismic motion from the total displacement, then you can find out the inter-seismic motion. So this is the inter-seismic motion here. This is represented by dashed line here. And when the next large earthquake occurs, completing the seismic cycle, everything to the right of the fault must have moved a distance vt. So this is what we have talked about. Just in the pre-seismic stage or the inter-seismic stage, what happens, the far side or far field material is moving and the material near to the fault is not moving. As soon as the earthquake occurs, the material near to the fault also catches up to the far field side motion. And you can see here the earthquake's co-seismic displacement will be given by this particular equation here. This is the uy is equal to plus minus capital D by 2 minus D by pi tan inverse y by w. D is the displacement, that is Vt, and w is the width of the fault. And the co-seismic slip uy is less than D except at the fault. So you can see like during the co-seismic motion, the D displacement occurred, and the displacement as you go away from the fault side, then it will be smaller than the displacement near to the fault, that is capital D. So this is what it is written here. The co-seismic slip uy is less than capital D except at the fault. Points away from the fault already have moved part of the distance capital D before the earthquake. So if you look at this co-seismic motion, so during the earthquake, this has moved a distance capital D here, and if you look at the point that are little far away from the fault, that let's for example this one, this has already moved during the inter-seismic stage, and during the co-seismic stage it will basically be moving a part of the distance capital D before the earthquake. Everything on the left side must have had no net motion from the seismic cycle, even though material near the fault moved backward in the negative x direction during the earthquake. So fault parallel, now we are talking about the inter-seismic motion, that is small less, that is as a function of distance y. Fault parallel inter-seismic motion Sy is found by subtracting the co-seismic slip from the far field motion, that will be given by this particular equation here. And you can see this figure here. So here that what we are talking about, this total displacement is given, and this co-seismic displacement is also given. So inter-seismic can be found out by subtracting the co-seismic from the total deformation. So material on the left side near the locked fault is dragged alone during the inter-seismic period and then rebounds during the earthquake. Material on the right side near the fault is retarded during the inter-seismic period and then catches up to the far field motion due to the co-seismic deformation. Now, if the fault is a plate boundary, the interseismic deformation occurs over a finite plate boundary zone within which sides on either side of the boundary move relative to the interior of the plate they are on. In this case, the boundary zone is relatively narrow, comparable to the depth to which the fault is logged. However, many plate boundary zones are broader because additional faults take up some of the plate motion. Because the interseismic motion is the difference between the far field motion and the coseismic motion that we just talked about, its variation with distance from the fault depends on the locking depth and the far field rate. Now we will see how the locking can affect the broader shear zone, or you can say if there is a shallow locking, that may basically result in concentrating the interseismic slip near to the fault, whereas the deeper locking spreads out into a broader zone. So you can see this is the fault plane here, and you can see like the shallower locking is concentrating near to the interseismic slip here, and the comparison with the coseismic slip shows that the width of the zone across which the motion changes rapidly depends on the locking depth. Now if we take the derivative of this particular deformation or the displacement, then we can probably find the strain rate, that is Exy dot, and that will be given by this particular formula. So if we, in the graphical form, if we put both the graphs of the displacement and the strain rate together, then we can make a certain analogy or the certain relationship between them. You can see during at the fault there is a sharp increase in the displacement here, and that will result in the higher value of the strain rate, and then you can see will be a peak here somewhere. So this is basically related to this. And the strain accumulates near the fault during the interseismic period and is released in large earthquakes. Like the displacement, the variation of strain with distance from the fault depends on the locking depth and far field rate. The strain rate can be inferred from changes in the angles between the geodetic markers. So now let's talk about the interseismic vertical motion due to a logged fault at a subduction zone. So this is the figure of the subduction, and you can see during the interseismic stage what will happen. There will be a landward motion, and then for most of the sites above the locked fault, this is the fault where it is logged, and there will be uplift happen due to the fault is logged in the inward land side, or you can say in the landward motion. And when there will be a rupture at this particular zone, and the energy will be released, and then you can basically make out that the geodetic data near the trenches can identify the interseismic deformation and provide insight into the mechanics of the subduction interface and future large earthquakes on it. Now let's have this example here. For the GPS velocities relative to the North America for sites near the 1964 Alaska earthquake rupture zone. So here this figure shows the GPS velocities relative to the stable interior of North America for some sites near the rupture zone of the great 1964 Alaska earthquake, and sites to the right, this is these sites to the east and the west, you can see. So in the western side it is basically moving in this direction toward the subduction zone, and in the left hand side this is moving in the opposite direction. So site to the east of the area shown move northwest in the direction of the Pacific plate subduction beneath North America, as we would expect for the interseismic motion of sites on the overriding plate above a logged fault. The motion decays rapidly landward with distance from the trench. You can see these are decreasing here. These are the smaller vectors here. The motion decays rapidly landward with distance from the trench. These observations, together with the observed uplift, are reasonably consistent with the interseismic motion. Now let's talk about the advantage of geodesy. In general, geodetic data for interseismic period give insight into the mechanics of a fault and future earthquakes on it even before they occur. This is gratifying because the seismic cycle is so long, typically hundreds of years, that we generally have to wait a long time to study a major earthquake on a given fault segment. Consider measuring the rate v of motion of a monument that started at position x1 and reaches x2 in time capital T. If the position uncertainty is given by its standard deviation sigma, then the propagation of error relation shows that v is equal to x1 minus x2 by capital T. That will basically be sigma v is equal to under 2 sigma by T, where sigma v is the uncertainty in the inferred rate. Thus, the longer we wait, the smaller the velocity uncertainty becomes, even if the data do not become more precise. The geodetic data let us see the rate at which logged slip is accumulating, hence infer the maximum possible slip in a future earthquake depending on when it occurs. We can also estimate the time until a future earthquake from records of past earthquakes by assuming what the co-seismic slip will be. And in some places, the geodetic data imply that slip is accumulating on the log fault at a rate less than the far field motion. And this difference seems to be due to the plate motion taken up elsewhere. And this is thought to indicate that some of the plate boundary slip occurs by aseismic slip or sliding, perhaps as silent earthquakes on the fault, and hence will not appear in the future earthquakes. Now look at this figure. Here we are showing the horizontal and the vertical GPS velocities relative to the North America at the site. And then you can see this is the model, and for which these GPS synthetic motions for the vertical and the horizontal velocities are developed. So you can see these solid lines are the synthetic ones, and this is also the synthetic one. This is the horizontal GPS velocity, this is the vertical GPS velocity, and this is the model. And what we observed here, that the horizontal velocities are matching quite well. Also the vertical velocities are matching quite well with the synthetic data. And in that case, in the vertical case, the uncertainties are more if you compare it with the horizontal velocity data. So the profile of horizontal top and the vertical center GPS velocities relative to North America for the eastern sides. The data are reasonably similar to prediction, solid line, for a logged fault model that is given at the bottom. Plate interface has a shallow dip, so there is a large fault area at depths shallow enough to accumulate strain and then rupture. Now let's have a summary of today's lecture. Fault parallel interseismic motion Sy is given as Sy is equal to d by 2 plus d by pi tan inverse y by capital W. The coseismic slip Uy is less than d is equal to Vt except at the fault. Interseismic motion is the difference between the far field motion and the coseismic deformation. Its variation with distance from the fault depends on the locking depth and far field rate. Interseismic shear strain rate, that is E dot xy is equal to half ds by dy is equal to V by 2 pi W 1 by 1 plus y by W square. Considering measuring the rate v of the motion of a monument that started at position x1 and reaches x2 in time capital T, if the position uncertainty is given by its standard deviation sigma, then the propagation of error relation shows that v is equal to x1 minus x2 by t. That implies sigma v is equal to under 2 sigma by capital T, where sigma v is the uncertainty in the inferred rate. So these are the references. With this, we are at the end of module 10. Now we will start module 11, where we will be talking about the magnitude scales, earthquake statistics, source spectra, etc. Thank you very much. Bye-bye.